Hello, good evening. This is Emmanuel, and I'm going to be discussing the topic predicting anti-cancer peptides using binary tree growth-based transformer and structural feature encoding with deep hybrid learning. So, um, thank you all. Thank you for joining me. So, I'd like to begin by introducing the topic. So, number one, um, sorry, uh, my network was a bit uh, off, but I just wanted to give a brief introduction on why this is why this research is necessary. So, as we are aware, cancer is a significant threat to human life and health, and according to the Global Center Statistics of 2022, about 20 million new cancer cases are diagnosed annually. And in the case of deaths, we have about 1.9 million deaths. This is in the US alone. So you can only imagine what that number is global or worldwide. So while traditional cancer treatments like radiotherapy, chemotherapy, and all the other different kinds of therapy still remain very, very valid in the fight against cancer, these methods have been found to be limited in some aspects. For example, there's a high risk of recurrence. Uh, it's very common that we treat people for cancer, but after a while, it remanifests. So we have such cases. We also do have limited effectiveness due to risks. I've already mentioned that. Severe side effects, including nausea, loss of hair, those are quite very common. And so, as a result of all these all these effects from the traditional treatments, cancer treatments, this has given way for development of new strategies in order to fight cancer. And today we are discussing anti-cancer peptides. So anti-cancer peptides are specific peptides that have the ability to fight cancer. So what we are trying to accomplish here is to be able to build a model that will be able to predict the anti-cancer peptides and those that are not anti-cancer peptides. So in other words, we're going to be doing a classification task here. So let's start by understanding the problem. Like I've already mentioned, our goal ultimately, or the goal of the authors in this who developed this hybrid model, was to classify peptides as either anti-cancer or as non-anti-cancer peptides. Now, this is crucial because the anti-cancer peptides have potential to treat cancer, like I've already mentioned. Now, however, predicting these peptides is not straightforward, and existing methods or models that have already been developed have quite a number of challenges. Kindly just allow me. There are some challenges that existing models that have been used already to develop or to fight, to try and predict these anti-cancer peptides have. Number one is including inadequate encoding methods. This is basically the process of converting the different sequences into numeric values that our models are going to be able to understand. So we have limited or inadequate encoding methods that have been applied. We also do have limited training efficiency. These models have not been exhaustively trained, in other words, or tested. And so part of that is generalization. The generalization power for these models is not very sufficient. And then we also have the issue of interpretability. Like I've said, since the training may not be very efficient, the interpretability that has been applied is not sufficient. for us to apply the same in all maybe bioinformatic tasks. And then the computation cost for the existing models is very high. And so those are the challenges that gave birth to this hybrid research model. Now, the approach that is used here is we have this prot-b-bart, which is basically like a word encoding technique, which is used to contextualize information and understand relationships between words and text. So they try to contextualize or understand the relationship between the different peptide sequences. And then we also bring in the composition and we bring in the composition, transition, and distribution techniques, which is used to break up to combine different small components and to get meaning for our peptides or for the relationships between the peptides. Now, that is at the point of doing feature extraction. Now, when it comes to feature selection, all the authors employed a binary tree growth algorithm, which is basically dividing the data into different branches, and then at each division or after every step, they go ahead and process the more informative branch. So that is the approach that was used. And then for the training, they used the hybrid of convolution networks and recurrent networks to try to improve the predictive accuracy of our models. So here we have the architecture, the neural network that was used. We have the convolution networks on this end, and then we have the recurrent networks. So the input that is taken here comes down, and then each of these produces its own different output, but we concatenate all this. And then use from this dense layer, we generate a sigmoid function that will give us a single prediction. Yes. So this is our architecture. We have the hybrid model, which captures contextual and semantic information. And then we have the deep learning architecture down, which involves this CNN and RNN layers to process the output, to process data in order to give us outputs that will ultimately use to make our prediction. Now, when it comes to the general flow, the approach they took was encoding, which is basically converting data into numeric values or sequences, converting the peptide sequences into numeric values, and getting relationships, patterns between that data. Next, the binary tree growth algorithm was used for feature selection in order to optimize the feature set. And this algorithm grows a binary tree by selecting features that maximize the information gain. Like I'd already said, we go with the branch that is more informative about our target, what we are trying to do. And then the selected features and then processed by the deep hybrid CNN and RNN. Now, it's important to note that after our encoding, we ended up with about 1063 dimensions. The probability here gave us 1024 after tokenizing and then breaking down the different sequences, peptide sequences. And then our composition features here gave us about 39 features, which we ended up with about 1063 different features. Now, we had to improve our selection of these features because not all of them were meaningful. And so when we employed this binary tree, we ended up with 149 features, which were mostly used to train the models and to train the hybrids of the models. Yes, so the training the models involved supervised learning, where we used labeled data sets. There were 2 training sets. They were used to minimize they used this to minimize cross entropy loss through back propagation and gradient descent. And the resulting model was a very capable and satisfying model, at least from the results of what they shared. So here I have an image of peptide embedding for feature extraction. This was using this probability model where we take input, tokenize, and then we have this SEP is basically like a delimiter, you could say. So if you have text like, I want to go full stop and then another sentence. So the SEP here acts as a delimiter. But in this case, since we are dealing with peptide sequences, so it's basically sequences to help us analyze patterns. Then we did have the self-attention layer from which we get the 1024 different dimensions of features. So I just wanted to highlight that, and then visualization of the extracted features. So at this point, this is A, B, C, and D. When we employed the probability model, this is how it looked like. This was on the probability model. This was on getting my words. But yes, when we employed the probability model, this is what we had. And then when we employed the CTD features, we had this. Now, when we had a combination of the probability and the CTD features, we noticed that there was at least there's overlap of the different features of feature selection. However, when we introduced our binary tree growth, there was a clear distinction between the features, meaning our predictive model accuracy is going to be higher because after applying binary tree growth, we clearly noticed a very significant change or difference. Yes, so that was the architecture, and that is how they selected features in order to train the models. Now, when training these models, they trained against training datasets, and the results were actually quite amazing here. The accuracies, they trained using traditional machine learning classifiers, and then they trained using individual separate CNN and RNN models, and then they trained using hybrids. Now, the results of these trainings or performances of different models are here, but just a summary. The accuracies of the traditional machine learning classifiers ranged from 63 to 75. We used the performance metrics we used were accuracy, the area under the curve, specificity, and sensitivity. Now, in this case, for this summary's purpose, all that data is captured here, but for the purpose of this, I just wanted to highlight the accuracies. So when we trained these models, or when we trained these models using traditional machine learning classifiers, this was the accuracy, and this was the area under the curve. As we know, this is supposed to be a value between 0 and 1, which is not bad. However, it could be improved. Now, when we use the different deep learning models, the CNN model achieved an accuracy of 81.83% and area under curve of 0.89, and the RNN obtained an accuracy of 84. However, when we combined the CNN, the convolution network, and the recurrent network, there was a very, very highly significant improvement, which achieved a specificity which is correctly predicted values negatively. It predicted correctly. It accurately predicted negatively that 96.77% of the data in our training sets, and the accuracy of 92.62, which was a very big, which was a sign that this was working. Now, when we went on to analyze the performance of this model against the Bluetooth feature selection using the training datasets, like I'd mentioned earlier, we use the feature, the blue tree, the BTG feature to filter or to select the different to select our most highly discriminative features. We ended up, the results are attached here as well. But as you can see just from a summary, this is the classifier, this is the encoding method that was used. We used the hybrid vector and the results are here. And once again, you see, while all the rest are not bad, you could say, but the highest accuracy was obtained by using a combination of the CNN and RNN networks. Continuing on, our predictive analysis of the independent data sets. Now, this was the data, the independent data that we used now to test final accuracy of our model that was built using a hybrid vector from both the ProBT model and the CT composition, distribution, and features. Now, when we examine it against there are three data sets. When we examine it against the first data set, independent data set, like I said already, machine learning models, the traditional machine learning models support vector machines, ERTs, SVMs. Their accuracies range between 79 to 85. Individual deep learning models, the CNN and RNN, their accuracies were between 89 and 90. However, when we brought a hybrid of the CNN and RNN, the accuracy grew significantly to 94.2%, as well as the area under curve was 96. That was on dataset 1. Dataset 2, we can see as well the information, how it transpired. Still telling us that this was a powerful approach to approach this. Overall, I can say that the model performed well, and this was very well. This was evidently shown in the results I've just shared, and which also gives us more, it makes generalizability easier as well. Now, when you go to results and performance, compared to the existing models that were shared in the paper, here as well, we can see significantly our data set did well. Now, the effectiveness of the proposed solution. First, I see high accuracy as the model achieved outstanding results on both the training and independent data sets. Two, it addresses key challenges, which is feature generation. We attempted to reduce reliance on lengthy evolutionary feature generation. And then for the case of sequence order information, the hybrid architecture effectively captured patterns. So that was, it addressed those challenges. And then practicality provides a reliable tool for predicting SCPs, accelerating drug discovery, and peptide-based therapeutics. Innovation approaches used. As we already see, they used for feature extraction, they used probability model for semantic analysis, and then they used this composition for structural features. And then the BTG-based approach, which was to optimize or to scale down to narrow down our features to select the features to use. Then for the case of training the models, we used deep hybrid, which is innovative, using combining the power of CNN and then RNN. And then these technologies have already been used by others. So it's the transformer-based model, using it is quite good technology and good techniques to use. Limitations. Despite the optimization, the model may still require significant computational resources for large-scale datasets. While one of our objectives was to achieve low computational complexity, when you look at the performance of these models, if you are to put these models, if you give them bigger datasets or maybe even more complex, while our interest may be to reduce on computation, that may be hard to achieve given the time intensity of some different architectures that may be required. And then generalizability, the model is tested on specific datasets. Its performance on diverse and unseen datasets remain unverified. Further validation is needed to ensure its applicability to other bioinformatics. So, for example, this model, we can only, so far it's only been proven on this data for which it has been trained. We need to get maybe other similar data and feed the data to it and see how it performs. Data which may not necessarily be about ACPs. Interpretability, the use of deep learning techniques, particularly transformers, makes the model less interpretable. Understanding the decision matrix of the model is challenging because we have very many different, what can I say, combinations, or we have hybrid in terms of feature extraction, feature selection, training the model. So identifying how the model is deciding or making its decisions may be a bit hard. Dependency on feature selection, the effectiveness of this BTG feature selection depends on the quality and diversity of the input features. Poorly selected or redundant features could impact performance. In conclusion, I try to come up with strengths, weaknesses for the paper and the review. High accuracy, and the paper or the model that was developed provides a high accuracy and robust performance across multiple datasets. Innovative hybrid approach combines state-of-the-art techniques and it addresses key challenges in SCP prediction. Weaknesses, computational complexity and resource requirements, like I've mentioned, if we were to do maybe other different, more time-intensive or larger datasets. Limited generalizability to diverse datasets. We need to test this model under other non-SCP datasets, then we shall have a good understanding, as well as interpretability. Future direction, this will have to do with the weaknesses that I've already stated earlier. Optimize it for large-scale applications. Validate the model on diverse datasets to improve generalizability, and explore internal interpretability techniques to enhance model transparency. Thank you. That's all I had. And yes, thank you.